Today, let's look on the multiple interfaces where you have different layers. Look for this simple case where we have three layers. The seismic signals travels from the source, moving all the way through these all three layers and get reflected back to the geophone. When you try to draw the graph may be the graph of x of time against the distance from the source, which commonly can be known as t against x. If you draw the graph of the time against the distance, you'll get the graphs because they are three layers. You'll get you have three interfaces, and therefore you have three graphs which are curved. Maybe this way for these three layers. If you use the green method to draw the graph of each of these, we get, of course, the velocity and the thickness. I mean, the green method, if you draw t squared against x squared, then you have straight line graphs. Then the slopes of this graph will give us the velocity of the adjacent of each layer, but that velocity will not exactly be the velocity of that layer, but just the root mean square velocity of each layer. But how can we get the specific velocity of each layer? Maybe the velocity of the first layer, the velocity of the second layer, and the velocity of the third layer. How can you get them? Well, DIX developed the equation that is known as DIX equation to find the expression of the total velocity encountered by the seismic signals in traveling through its way. How does it work? Well, DIX equation says that the root mean squared velocity for this three layer, the square of it will be the same as, look to these three layers. First layer has velocity v1, second layer has the velocity v2, and the third layer has the velocity v3. Then Dix said that the root mean squared, I mean just like the summation of the velocity, the net velocity of the encountered by the traveling seismic signals will be given as the root mean squared velocity. The square of it is equal to velocity of the first layer squared times the two-way vertical travel time. When I say two-way vertical travel time, I mean the time taken to cover the vertical distance. This is the one-way travel time. And of course, this is the one-way travel time for a certain layer. The vertical travel time, the one-way vertical travel time for the first layer is this one, change in T1. This, I mean, from the surface to the first interface, the time taken to move is changed in T1, meaning the vertical travel time for the one-way vertical travel time for the first layer. Then you plus the velocity of the second layer squared times the vertical travel one-way vertical travel time of the second layer, then plus the velocity of the third layer squared times the one-way vertical travel time of the third layer. Then you divide the summation of the total vertical travel time of all layers. So this is the DIX equation. So general DIX equation can be written as general. Now the DIX equation can be written as, so the root mean squared velocity for nth layer squared will be the same as the summation from I is equal to 1 to I is equal to n, the summation of velocity of a certain layer squared, then times the vertical travel, one-way vertical travel time of that layer, divide by the summation of the vertical travel time from I is equal to 1 to I is equal to n. So this is the DIX equation. How can this DIX equation help us furthermore? Let's simplify this formula into a simple way that can be memorizable and that can be directly useful. So now this equation can be rearranged. If you multiply the denominator each side, you will get the root mean squared velocity for the nth layer, the root mean squared velocity for the nth layer, then you multiply by the summation of the one-way particle travel time from I is equal to 1 to I is equal to n will be the same, will be equals to the summation of the I is equal to 1 to n vi squared change in gi is equal to the, we can let this as the equation number 1 up to there. Again, if you can further rewrite this equation as follows: summation of the one-way vertical travel time I is equal to 1, I is equal to n will be the same as this term here. Remember mathematically, if we say, let's find a space to write something. If we say mathematically, if we say that the summation of the of the item may be, if I is equal starts from 1 to n, is the same as summation of ui, I is equal to 1 to n minus 1, then plus un mathematically. And therefore, to our question also, this one here, this term can be expanded in this way, that you take the term behind this one, which is n minus 1, I is equal to 1, vi squared change in ti, then you plus vn squared change in tn, this one here. And this is the equation number 2, let's say. But also, from this, the expression for root mean squared velocity, as we have seen here. Now, if we write for n is equal to n minus 1, this root mean squared velocity for the term of n minus 1, root mean squared velocity will be given as the summation of velocity I squared change in ti. I starts from 1 to n minus 1 over the summation of the one-way vertical travel time I is equal to 1 to n minus 1. Of course, again, if you rearrange this one, multiply the denominator each side, you have the root mean squared velocity for the term for the n minus 1 layer squared. You multiply by the summation of the one-way vertical travel time is equal to 1 to n minus 1 will be equals to the summation of vi squared one-way vertical travel time I is equal to 1 to n minus 1. This can be equation number 3. If you look careful to this equation Roman 3 and look again into the question number 2, you will find that this term here, which is expressed in this way, is also found within the second equation, this term here. And now you can make the substitution. Now substitute equation number 3 into equation number 2. If you make the substitution of this equation, of the third equation into the question number 2, then it will look as follows. It will be the root mean squared velocity for the nth layer times the summation of the one-way vertical travel time is equal to the summation of the root mean squared velocity for any minus one layer, squared. I is equal to 1, I is equal to n. Then you multiply by the summation of the one-way vertical travel time for I starts from 1 to I is equal to n minus 1. Then plus the velocity of the nth layer squared times the one-way vertical travel time of that layer. And now we can make this Vn the subject of the formula, and then the question is the question will look as follows. Vn squared is equal to root mean squared velocity for the nth layer squared summation of the one-way vertical travel time I is equal to 1, I is equal to n, minus the root mean squared velocity for n minus 1 layer squared times the summation of the one-way vertical travel time for I starts from 1 to I is equal to n minus 1. So this is the root mean squared velocity. And now the question will look like that one. Then you divide by the one-way vertical travel time of the nth layer. This is generally, of course, the equation useful. But remember, this is the summation of the one-way vertical travel time. One-way vertical travel time is equal to two-way vertical travel time divided by 2. And therefore the summation of the one-way vertical travel time for I starts from 1 to I is equal to n is equal to, remember, two-way vertical travel time, we say that is 2 naught. If you remember, 2 naught was expressed as 2h. If you remember, 2h you divide by velocity, of course. 2h means to move h downward and move h upward. Therefore, t naught is the time of the two-way vertical travel time. And therefore, the summation of the one-way vertical travel time will be given as two-way vertical travel time of the second layer, okay, minus the two-way vertical travel time of the first layer. Then you plus, but over 2, of course. Then you plus the two-way vertical travel time for the third layer minus the two-way vertical travel time for the second layer over 2. The summation continues until the two-way vertical travel time for the nth layer minus two-way vertical travel time for the layer below it or before it, then over 2. If you open this, if you sum it, you will finally end up getting that, or discovering that the summation of the one-way vertical travel time for I is equal to 1 to I is equal to n will be the same as t naught n over 2. If you will proceed in making summations, some terms will cancel. You find this one will cancel with this one, and this one will cancel with the term behind it, and therefore you will remain with the two-way vertical travel time of that layer. But also the summation of the two-way vertical travel time for I starts 1 to I is equal to n minus 1 will be the same as t naught n minus 1 over 2. Similar fashion like this one here. And what about the one-way vertical travel time for the nth layer? This will be the same as the two-way vertical travel time for the for the nth layer minus the two-way vertical travel time of the layer before it, divided by 2. So if you take this term here, and this one, then substitute to our equation here, then the question is modified to this form. It will be given as the root mean squared velocity squared, then the summation of the one way vertical travel time will be equals to this one for this, then this one for this, and therefore times t naught n over t n minus the n minus 1 root mean squared velocity t naught n minus 1 over 2. Then you divide to this one term, substitute the value of this term is this one here, will be t naught n over 2 minus t naught n minus 1 over 2. And therefore our equation will be given as Vn is equal to the square root of the root mean squared velocity of that layer, root mean squared velocity multiplied by t naught n minus Vn root mean squared velocity t naught n minus 1 over t naught n minus t naught n minus 1. So this is the expression for the nth velocity of the nth layer. If the layer is, but the values of root mean squared velocity will directly be obtained from the graph, and these two-way vertical travel time are obtained from the graphs. So if you draw the graphs of the three layers, layers by using the green method, by green method you will get the straight line graph. From each graph you will extract important values, the root mean squared velocity of the first layer, root mean squared velocity of the second layer, and the root mean squared velocity of the third layer. And also from these you can get the t naught. T naught are these intercepts. So you will be substituting and get the velocity of a particular layer. Thanks for watching. Just keep following my series to share this knowledge. If you are the new to this channel, please subscribe to get more details. Thank you.